To align with environmental sustainability practices of today, a new or expanded strategy to the approach and treatment of residual end-of-life materials is necessary. Our focus today in Recovery 2.0 will be on the thermal reduction process, used for the recovery of individual elements from residual waste streams. Recovery 2.0 provides an opportunity to learn how to manage resources in a sustainable method by treating waste as a resource, while assisting with the world's demand for clean water and clean energy, using thermal reduction. Recovery 2.0 utilizes heat to perform the thermal reduction process to vaporize waste water and solid waste materials into a gaseous state and a recovered solid fraction. This type of waste decomposition is a method that allows the recovery of basic molecular elements. The waste vaporization process involves a phase change in the feedstocks and the conversion into the various output products. Recovery 2.0 uses a pyrolysis system as a processing method designed not to release open emissions, but rather operates on a mass balance equilibrium basis where the output products are captured and recovered. The thermal reduction process utilized by Recovery 2.0 involves a two-step thermal reduction process, the heating stage and the pyrolysis stage. The heating stage harnesses a primary heat source in a separate reverberatory chamber and transfers that heat into the pyrolysis chamber. The pyrolysis stage is performed in an oxygen-starved restricted air free flow environment, designed to prevent combustion and the production of unwanted combustion byproducts. Heat in the pyrolysis chamber is elevated past the point of vaporization of the waste feedstocks, which may then be captured directly into the Recovery 2.0 working fluid pipelines. The pyrolysis system outputs are largely determined by the pressure, temperature and dwell time within the pyrolysis chamber and are captured in order to achieve or maintain a mass balance equilibrium. Any primary heat stage emissions that may be generated are contained in a separate pathway and are recovered or regenerated. The working concept behind the Recovery 2.0 system is to design a functioning process that provides flexible options as to the pathways, incoming waste feedstocks, and product outputs, and to provide the ability to swap from one to another as seamlessly as possible. In regards to the choice of primary energy sources, the design needs to accommodate intermittent alternative energy sources, while maintaining reliable and redundant production. The flexibility to operate or switch between multiple sources that may run on a side-by-side comparative basis allows for an innovative and comparative environment to advance and develop improved methods and technologies. Operating multiple independent thermal reduction units simultaneously provides a unique opportunity to create unprecedented symbiotic efficiencies. Options for sources of heat in the thermal reduction process range from combustion of fossil fuels to bioenergy renewables with emission capture. The use of solid recovered carbon as a green coal substitute may be an ideal use case as a heat source. Exploration of carbon-free heat sources may be a desirable option with the use of alternative energies such as clean electricity, hydrogen or concentrated solar, or more exotic options including plasma arc energy. Whichever primary energy source is chosen, the Recovery 2.0 system relies on a multi-stage energy recovery process. An insulating envelope surrounding the thermal reduction units may maximize the heat recovery potential. Types of heat sources that are available for use in the thermal reduction process are solar, electricity, microwave, plasma arc energy, oxy-combustion, exothermic energy extraction, and other recovered, harvested or alternative energy. Wherever possible and geographically feasible, the use of concentrated solar energy, as a source to generate a high heat, sufficient to drive the thermal reduction process makes sense. Thermal solar energy may be focused onto a receiver that is designed to convert a thermal media into a high-temperature heat transfer source, adequate to perform the pyrolysis process within the thermal reduction chamber. Any excess heat that is generated may be sent for thermal energy storage or may be used to generate electricity. There are several opportunities to extract heat or electricity by light energy harvesting. An electrical heat source may be acquired on demand from electric heat or radiant or induction heat. Electricity as a heat source has flexible variable temperature control. Electricity may be tapped into from the internal energy management control system and dispatched as prioritized. The thermal reduction of waste materials using microwave energy as a heat source may be an efficient pyrolysis process since you heat from the inside out. There is no need to heat the outer shell infrastructure of the furnace. Focusing direct heat on the waste feedstock will quickly pyrolysize the materials into a vaporized hot gas and a solid residue fraction. Different waste feedstocks may be more or less receptive to microwave stimulation, requiring the aid of a catalyst to enhance the focused molecular stimulation. In some cases, the blending of waste streams may achieve the same result to replace the catalyst. In the early 1990s, we would typically dose the incoming feedstock with recovered pyrolysis oil to kick-start the speed of the reaction time. One interesting source of heat to drive the thermal reduction process is plasma arc energy. Plasma arcs generate extreme high temperatures that can be focused on targeted localized areas. An electric arc causes an ionic plasma reaction in the immediate surrounding environment, typically air or some other pre-selected gas, which results in emitting heat in the order of several thousand degrees Celsius. Typical plasma arc systems may not be a two-stage design. The electrode arc or plasma torch are commonly applied directly within the pyrolysis chamber. The extreme high energy and heat causes the waste materials contained within the pyrolysis chamber, or gasification furnace, to instantaneously vaporize. This high-temperature vaporization may require some additional cleaning and refining steps if the plasma arc draws in air from the ambient atmosphere. Also, the electricity source used to generate the plasma arc heat is a critical factor in this method of thermal reduction. The use of an oxy-combustion process, combined with emission confinement and regeneration systems, are a viable strategic method of driving a thermal reduction operation with sustainable fuels. Fuels used in the oxy-combustion process are hydrogen, carbon, and hydrocarbons. The use of hydrogen as a primary energy source to begin the thermal reduction process is made possible by hydrocarbon splitting. Harnessing hydrogen energy as a fuel to heat a thermal reduction process provides an opportunity to evolve methods of combining carbon and hydrogen, in the absence of oxygen, to produce the required heat and a hydrocarbon output. This output may be cycled for the regeneration of clean hydrogen. Recovered solid carbon represents the largest share volume of recovery yields from mixed waste streams. The oxy-combustion of recovered carbon provides a huge opportunity to develop a sustainable economy, based on an environmentally contained centralized or decentralized regeneration cycle for waste treatment. The recovery of materials from a mix of various waste streams results in a wide range of results depending on the contents of each individual waste stream and its source. The trends tend to be somewhat consistent for the types of waste streams generated from the same sources. Most mixed municipal solid waste streams contain mostly a variety of plastics, paper, food and organic wastes, which at their fundamental or elemental root, are just a mix of carbon, hydrogen, and oxygen. This group of basic building block materials altogether are classified as types of hydrocarbons. The recovery of these hydrocarbon materials provides an opportunity to develop a range of intermediate products that may be used as sustainable fuels to replace traditional fossil fuels. The use of exothermic energy extraction is a method of harvesting heat to drive a neighboring endothermic process. Exothermic heat is generated from redox reactions where elemental bonds are formed. Our particular interest is focused around the oxidation and displacement process that occurs when refining metal oxides. A similar effect may be harvested from the hydrometallurgy process of dissolving metals in acid solutions in the recovery procedure. The process of forming hydroxides also provides an opportunity to extract exothermic heat during the recovery of minerals and salts. A variety of alternative energy sources and bioenergy renewables are also viable heat source choices. The choice of a select few fuel sources to provide the primary heat for the thermal reduction process may provide a unique solution through oxidation or controlled combustion. The oxidation emissions may be channeled into a closed pipeline and used as the working fluid and recovered into valorized products. A solid carbon or CO2 recovery cycle may be ideal for this application. In addition, syngas may also be an option. The option to use traditional fossil fuels exists, with a focus on the responsibility for the avoidance of combustion emissions. Current efforts have shifted towards the potential use of what is referred to as green fuels, such as syngas, renewable natural gas or methane. In the methanation process, also known as power to gas, carbon dioxide, CO2, and hydrogen, H2, is converted into methane, CH4. This is used as a direct substitute for traditional natural gas. Conversion into liquid fuels such as naphtha, methanol and ethanol are an expanding area of interest, particularly in regards to the production of transportation fuels like gasoline, diesel, and aviation fuel. Typical raw inputs of waste stream feedstocks in the Recovery 2.0 thermal reduction process fall into two main classifications: liquids or solids. The main volumes of liquids are in the form of brine and wastewater, while the solids are generally referred to as mixed wastes. The Recovery 2.0 system is based upon the full pyrolysis process designed to break materials down into basic elements, as opposed to partial decomposition that only reduces waste into complex intermediate products. Full or complete pyrolysis accommodates a wide variety of waste inputs, regardless of the calorific values, and may tolerate moisture contents of up to 100%. The input feedstock may be sourced from a wide variety of sources which will affect the content or mix of raw materials contained within that particular waste stream. This will determine the blend of product outputs. Typical pyrolysis outputs are in the form of both gas and solid fractions. The gaseous phase vapors that are produced are collected and processed in the hot gas refining system. The hot gas may be refined or condensed into a liquid fraction. The solid residues are extracted as a solid fraction for further processing. In summary, once the first stage of the thermal reduction process is complete, the feedstocks proceed to the intermediary stages of hot gas refining and high temperature refining. The materials are segregated into semi-finished output products. The challenge is to design for optimum operation by engineering a system that has the capability to swap from priority or default pathways as seamlessly and rapidly as possible, and the ability to scale up or down in each energy pathway module. Recovery 2.0 was developed by Waste.net as a system to manage resources in a sustainable method by treating waste as a resource. If you would like more information about the Recovery 2.0 process, additional videos are available and links have been provided in the comments, or feel free to reach out to us. Waste.net is a tool to assist you by matching waste material generators directly with beneficial users of those materials. By connecting you with market participants, we foster collaboration and promote environmental sustainability. Visit our website waste.net today to learn more. Let us assist you in your efforts to manage your waste. Waste.net may also be able to assist you in finding a market to buy or sell your scrap waste or byproducts.